Hi, algebra students. Today we're going to talk about section 6.2.3, which is called Association is Not Causation. So a study found that the more hours students spend on activities outside school, the higher their grades tended to be. Does that mean if you sign up for more activities, your grade will go up? Another study found a link between how often you brush your teeth and a reduction in heart disease. Does that mean if you brush your teeth twice a day, your heart will be healthier? As a consumer of statistical information, you need to be aware of the difference between association and causation. Today's investigation will explore that difference. So in 6-79, it says fire hoses come in different diameters. How far the hose can throw water depends on the diameter of the hose. The Smallville Fire Department collected data about their fire hoses. The residual plot for the data is shown below. Part A asks, what does the residual plot tell you about the LSRL model the fire department used? So remember we talked about the residual plot. If it shows like totally scattered data, it means that a linear model is a good representation of the data. If it's curved or seems to funnel, then it's probably a different model. Here I'm noticing that this is curving. So what this tells me is that a line is probably not the best model. So since the residual plot is curved, a linear model is probably not a good fit. All right, so then part B says, find the worst prediction made with the LSRL. How different was the worst prediction from what was actually observed? Explain why in context. So when it says which one is the worst, we're looking for which of these points seems to be the furthest from the x-axis, because that means the residual was like that point was the furthest from our line of the LSRL. So to me, it sort of looks like this one seems to be like the furthest away. So if I kind of go like this, it seems like, so if this is 2.5 and this is 2.75, so maybe this is like, we could estimate, we could say if we had a 2.6 inch diameter hose, the LSRL predicts that, and this is what are we comparing? How far the water can throw, predicts the hose will throw water. What is this? This is 22, that's 25, maybe about, let's say maybe 22 feet farther or further than it actually does. So that's what this point is telling us. So the residual is up about 22 at 2 maybe 6 or 2 maybe 2.6 sounds good. So this residual is telling me that the prediction is telling me that it goes further than it actually did. And in this case, I mean, that's kind of misleading information. So how we talked about sometimes a positive residual is good, sometimes a negative is good, right? In this case, I don't think that's really great. All right, so then 6-80, the mayor of Smallville finds the following graph in the town's annual financial report. Describe the association, if any, in the scatter plot. So just looking at the scatter plot, it's heading upward. So it would say it's positive, maybe moderate, positive, and it looks maybe linear, right? Like I could throw a line in here. So for the association, we would maybe say moderate, positive, linear association. Now, the mayor immediately orders the fire department to send fewer firefighters to each fire so that there is less damage. Why do you think the mayor said this? Do you agree with the mayor's decision? Explain why or why not. So Why could the mayor have said this? So, looking at the situation, it's the number of firefighters versus the amount of damage. So, he's seeing that it seems like this graph might be implying that as the number of firefighters increase, the amount of damage increases. And so, he might think, oh, I should send fewer firefighters because if then I would have less damage. And so, do you agree with this decision and explain why or why not? Now, that's your personal, opinion, whether you agree or not, and what your explanation is. I might think the reason there's more damage is, and they needed more fires is because, or firefighters is because maybe it was a more, like a bigger and a more dangerous fire, and so they needed more firefighters. And because the fire was bigger, that's really what caused more damage, not necessarily the number of firefighters. So when it talks about association versus causation, just because there seems to maybe be an association with these points that it's linear, it does not necessarily mean that the number of firefighters causes the amount of damage. So when you're reading graphs, you have to be really careful about that because it's easy to assume that. All right, so let's look at number 81. It says a dietitian studying the benefits of eating spinach surveyed a large sample of individuals. She recorded the amount of spinach they ate and then their physical strength. The dietitian found the spinach eaters to be much stronger than the non-spinach eaters. The next day, the newspaper headline was, Popeye was right, eating spinach makes you stronger. Do you agree with the newspaper? Do you agree that if you eat more spinach, you will grow stronger muscles and increase your strength? So again, this is kind of your opinion. So, eating spinach is good for you, but does that necessarily mean that if you eat more spinach, you'll grow stronger muscles and increase your strength? Is that the only reason why you could grow stronger muscles and increase your strength? So that's kind of your opinion right there. Then B says, the dietitian correctly found an association. So like if you were to graph, right, you might notice that as the amount of spinach increases, the amount of strength increases. And so you might see again like a graph similar to this. So that means they're associated. You might have a correlation coefficient that's close to 1. But does that necessarily mean that spinach is what's doing that? So this is asking what could explain this association other than that spinach makes you stronger. So it might be that people who eat spinach tend to make healthier choices in general, and maybe they exercise because they just have good habits, and that's what makes them stronger. So it's not necessarily they ate spinach, therefore they are stronger. So in 82, it talks about a lurking variable. It's a hidden variable that was not part of the study. So, for example, the size of the fire in problem 80 and the amount of people who work out in 81 are considered lurking variables. So you always want to kind of keep these in the back of your mind when you're looking at data. Like, are there other things that could have caused this to happen besides just whatever the independent variable is? So this last situation here, a medical study found a strong link between the number of hours high school students wear a helmet and the number of concussions or head injuries. However, it is unlikely that wearing helmets causes head injuries. Can you think of a lurking variable that might explain this association? So why is it maybe that people who wear helmets end up getting concussions? Because it's unlikely that wearing the helmet caused the concussion, right? What's the other thing that could be going on in that situation? So think of like, when would you wear a helmet? Maybe when you're skateboarding, maybe when you're playing football or riding your bike. And the risks that you take when you do those activities are what could be causing the concussions, not necessarily just the helmet. And so that's what you want to think of when you're looking at data, is not just association, but what's causing the association.